So we are the On A Leash group, and my name is Chikezie, Ezuma-Ngwu.
My name is Kulkarni.
So the overview of the Spot project is we are studying Spot of when he has a leash or not. We want to study how people react to Spot when they're moving down the hallway, Spot with a leash or not. Because we want to see how anxious they are, how comfortable, how fearful the Spot is, to better understand the relationship with Spot and the environment. Spot will be completely autonomous, so that the study could be repeated infinitely for anyone to do, and there'd be no errors from human mistakes, such as moving too fast or moving too slow.
So our motivation behind this project was that Spot is a popular quadruped robot that's being used in many different cases. In hospitals, it's being used as an intermediary for contactless patient to doctor care. It's being used in police departments for bomb defusal, hostage situations, and general patrol. And it's also being used in factories to monitor and predict any type of hazardous fires or any type of explosions. So we want to examine the general public's comfort with when Spot is held on a leash and when it's not, just because that shows kind of like a restraint against Spot is acting out. We kind of got this from there was an incident a few months ago in New York where there was a video that captured a Spot being used by the NYPD, and everyone kind of got freaked out by it just because it was the police department using a Spot, and they didn't feel how comfortable it was to have such a weird new technology being used like that. So how does our autonomy work? So we actually started off by prototyping all of the autonomy on a VWR bot. And our hallway lanes, we have a hallway that's split into 3 lanes. It's split by having 4 plotted points, and then we just get the midpoint to get the middle lane. The yellow lines that you see are the center lanes, just so it's more accurate for the Spot to go into the right lane. And how the logic works is if they're in the same lane, so if they're both in the left lane, the robot will move to the rightmost lane. If they're both in the middle lane, the robot will move to the left lane, and if they're both in the right lane, they both move to the left lane. So generally, the robot just tries to get as far away from the person as they can. Except in the middle lane, they can only go one direction. So, and to determine which lane the robot and the person are in, we're given a point. So whether it's the robot's position or the person's position, we have 2 vectors. One vector is from the bottom of the lane to the top of the lane, and the other one is from the bottom of the lane to the person or the given point. We get the norm using that formula, and we find the closest point in each lane, and then we just use a distance formula to figure out which is closest. And so in this case, it's closest to lane 2, so we'll just assume that the robot's in lane 2. And when we're going to switch lanes, we want to always be moving forward, no matter if it's switching lanes. So we don't want to make it an abrupt turn. So we have an offset of 0.5 meters that we always move forward in. And to calculate where the next point or the next point the robot needs to go to is we use the closest point that we got from the last slide, and we calculate our norm by using a distance formula just to get the x and y positions to go to the next step.
So now to track the person, we use an Azure Connect to gather data about the joints of the person, such as the head, the pelvis, the navel, the chest, etc. With that data, we change it into a TF frame, which we could see on ARGUS and also we could see on its implementation. And with the TF frame, we're able to measure the distance between the robot and the person. So at all times, we know how far that is. So if they meet a certain threshold, we can make a instance to move to switch lane or keep going on. And we had to make a cooldown variable for the Azure Connect because the polling rate of the Azure Connect was slower than the driver of the ROS node. So whenever we had the robot turn, we shut down Azure Connect so that when it turned, it didn't make the person's TF frame to move with the robot, which would therefore ruin our program. So how this all works as the robot's moving is we have the robot moving from the beginning of the hallway to the end, and we have it continue checking to see a person, and if it never does, it would reach the end of the hallway with no issues and halt. Now, if it does detect a person, it would first convert them into TF frame, figure out which lane they are, and then determine what to do with that person. If they're in the same lane, it will use the logic we described in the hallways to avoid them. If they're not in the same lane, it will try to pass by until it's reached the end of the hallway. If it does that after the person passes them, it will move out of the way. And it keeps going until the end of the hallway. Now, we felt like we did enough on BWI block, so we wanted to implement this on Spot. And one of the first issues we had with the implementation is the Spot autonomy doesn't support move-based goals. So we had to change all our move-based goals into twist messages. And with that, we just changed the X, Y, and Z coordinates using Kulkarni into twist messages. And in addition to that, the autonomy did not support G mapping. So we had to use a LiDAR-based mapping or a vector mapping to make a new vector map for the Spot to know where it is on the map. And in addition, and also Spot doesn't support ARVIS, or the computer doesn't support ARVIS with a GPU. So we had to upload our map to a web-based ARVIS where we could there see the visual data of the Spot as it's going down the hallway.
Yeah, and to test our proof of concept of how the rest of this autonomy was working, we used LiDAR instead of the Connect either, because the person tracking wouldn't work on the MacBook Airedale that's connected to the Spot right now. So as you can see, the robot realized that Parth was in the middle lane and chose the left lane to avoid the gliding. And then this is what it looks like on the web-based ARVIS. It's not as clear just because the LiDAR kind of started getting a lot of data from the top cars on the hallway and everything, but it recognized cars as walking towards him and decided to go to the other lane. So what's next? So we want to get the Spot laptop running. We have everything installed. We're just trying to get the last components to finish up working on the computer, and then we just need to plug in with the Spot and run it on that. That's the last test that we have to really do. Just make sure that the Spot can go from one side of the hallway all the way to the other by avoiding the person no matter what lane the Spot's in and no matter what lane the person's in. And then we would be ready to start the setting or the experiment with the leash and the leash.
And questions? What's the biggest roadblock to getting this deployed? What's the biggest roadblock to getting this ready to run the human study right now?
Honestly, I think we can get it done today. We just have to get the computer working.
Yeah, I think y'all are really close. I think that right now it's like having problems compiling live Connect hallway or whatever that Connect wrapper on the new laptop, because it was developed under 1804, and then to run the new laptop it's on 2110.
Like you look at distro and that just made for machines.
Yeah, there was some significant like 1804 is on OpenCV2, and now 2110 is on OpenCV4. So there's some real craziness in terms of getting everything to compile. But really close, so I'm pretty excited for it. Cool. Well, thank you all very much. All right. Okay.